Hello and welcome. Today we're going to look at how we can find the envelope of a family of curves. That's the tangent curve enclosing all the curves within a particular set. And to help us visualize what I'm talking about, let's look at an example. Say we throw an object, like a tennis ball, with velocity v at an angle theta above horizontal, and we'll ignore air resistance and say that gravity is the only force acting on it. So, depending on the angle at which we throw the ball, it will follow a different trajectory. And our goal is to find the envelope of these trajectories, shown here by this red line. And this won't require any complicated university level maths, just a bit of trigonometry and calculus, but mostly some careful thinking. So, to start with, we need to work out the equation for just one possible trajectory before we start worrying about the envelope. And to do that, let's first split the velocity of the ball into its x and y components. The initial velocity in the x direction is v cos theta, and in the y direction it's v sin theta. Now, in the x direction, there's no acceleration. The velocity is constant, so the displacement is simply v cos theta times t. But in the y direction, we have a negative acceleration due to gravity. So we can integrate that once to find the velocity, and again to work out the displacement. Great, so we've now got parametric equations for both x and y, depending on the time t. However, it's much easier for us if we can write y only in terms of x. So we need to find an explicit function y equals f of x. And in this case, since x is just a constant times t, we can substitute that in and get y in terms of x. And we get a negative quadratic, a type of curve known as a parabola, which is why you'll sometimes hear projectile paths referred to as parabolic trajectories. Okay then, so we know the equation of one trajectory. How do we go about finding the equation of the envelope? Well, in this case, the envelope is the maximum y value reached by any trajectory for a given value of x. And to find that maximum, we do what we normally do, differentiate. Except here, we want to know the maximum at any value of x, so we're not differentiating with respect to x. Instead, we want to know how the y value changes between different trajectories, so we're going to differentiate with respect to theta. And when that equals 0, we know that we've found our maximum. So I'll give you a few seconds to pause and have a go at that if you like. Otherwise, I'll show you the solution. So we differentiate with respect to theta, and we'll put the two terms on opposite sides. Then to tidy this up, we can cancel out common factors and use the fact that cos squared plus sine squared equals 1. And we get that tan of theta is v squared over gx. Not the nicest relationship in the world, but let's plug that back in and see if the maths works out nicely. So coming back to our old trajectory equation here, we want to make this substitution for theta. And it's simple enough for the first of the two terms, because we already have a sine theta over cos theta, or a tan theta there. But the second term is slightly more awkward. We've got a cos squared theta instead. So how can we deal with that? Well, again, we can use the fact that cos squared plus sine squared equals 1, and we can rewrite that bracket as 1 plus tan squared theta. So we can substitute in the second term as well, simplify things a bit, and we've got our answer, which is also a negative quadratic in x, which I guess isn't too surprising really. Although this equation is symmetric about the y-axis, which makes sense as the envelope should be the same in both the positive and negative directions. So that's a nice sanity check that we haven't made any obvious mistakes. I hope you enjoyed this video and found it interesting. Please do subscribe if you'd like to see more. Thanks for watching, and I'll see you next time.